Hey guys, welcome to the third part of the Transformers playlist. And today we're going to be talking about decoders and its outputs. So let's get right into it. This part will be a little bit different because normally I explain a part and then give you the code. But this time I'll give all the code at once because if you'll notice soon that all the codes are actually pretty much the same as the previous one with just a few minor changes. So that's why I'm going to keep all the coding to the end and I'll just explain all the content, the theory part for now. So let's get into it. Hey, now if you take a look at this diagram might be familiar. We talked about this before. So we've covered the encoders, we've covered all of this. This is the encoder part. Now we'll be focusing on this, which is your decoder. So your decoder is up to here actually. So this part, this region here is your LM head. And this right here is your decoder. Now if you look at it, it's mostly the same as the encoder, except we've got a masked multi-attention head over here, and we've got something here known as a cross attention head. So don't worry, I'll get more into it later, but just know the last encoder block, the value from it, its output is fed as the key and the value, and the query is taken from here. And I'll explain why we need masked attention, but don't worry about that. I'll get into that very soon. And the rest is the same. We've got a feed forward, we've got a layer norm, and then again this LM head, very simple. I'll explain it in a bit. So without further ado, let's get into this part first, the output embeddings. Let's see what exactly gets fed into the decoder. So let's get into the output embeddings. So right here, as we can see, we've got a text input. This input here is the morning was calm, dot dot dot. You can read the paragraph, and your target is the summarized text, which is essentially the quick brown fox jumps over the lazy dog. Now, normally what happens is, remember we talked about context lengths. So the context length of an encoder is generally much bigger than that of your decoder. So let's assume that our encoder has a bigger context length and it takes in this full chunk of input. Actually, it'll take in the tokens, but for now, let's just work with strings so that it's easy to understand. So it takes in the entire thing, and you've got your matrix, you've got your masked attention. So this whole part, this input part rather, let me draw it in green. This whole thing will get fed into your encoder. So your encoder gets this, and all your positional embeddings and your input embeddings are calculated based on this. Now your decoder, on the other hand, works with your targets. So it works with this part. So assuming that we have a context length of 3, we have to implement the sliding window protocol, and I'll show you how that works. So essentially what happens is your decoder input is going to be, let me just write input. Yeah, decoder input, and your target. So it gets divided in this format. So you will add a start token. I'm just going to name this as the start token. And since it's a context length of 3, so it's going to be S, the quick, and your target here will be the quick brown. Then for your next window, let's just call this window 1. Your second window, this will be it. And your target will be quick brown and then fox. So this is what your loss function is calculated on, your target, but your decoder input, the one where you get output embeddings, is essentially just this. And your positional embeddings are the exact same as that of your encoder, so we don't have to worry about that part. So we just need to break this down into this format, and this runs the entire time. So for one, let me clarify what I mean by that. So your encoder takes this full thing and it computes it, and once it computes the attention and you get the encoder output, then only your decoder starts firing. And in your decoder starts firing in these windows. So you'll have one window here, two windows, and let's say in total you have, let's say, 4 or 5. Let's just take 5 windows. uh, Again, I'm just simplifying it here. I'm not getting into the exact details, but essentially you'll have a certain number of windows, and once all these windows are covered, that's your decoder output, like your first iteration's output of your decoder. So that's how that works. And now I'm going to explain masked attention. So the reason I explain this decoder input and the target is it'll make more sense when we talk about masked attention. So let's get into that. Let's take a subset of the previous one. Let's just take the quick brown. Now our decoder input is essentially the words, the start token, the quick, assuming context length is 3. And the next thing we need to do is predict brown. So our decoder takes in these inputs. Now, if you remember the attention process, ultimately we get a matrix, right, of context length by context length. So we get S, the start token, the quick. We've got our similarity matrix, your start, the and quick. And it fills in with whatever values. You've got a 3 by 3 similarity score matrix. Now, you must realize that there is some issue with this. When you have your start token, you don't have the knowledge of the and quick. And then when your model gets the next context, which is the word the, it can see into the future essentially. It can look at quick. So this is what happens. But your start token should have no relation with its future. If you do that, you're essentially cheating. You're letting the model already know what the answer is, what it needs to predict. So your training loss will be 0 essentially. And during inference, your model will perform horribly. So how do we fix this? So we fix this using masked attention. So essentially what we need is, so when we have start, it should have no knowledge of the future. Then when we get in the, it should have no knowledge of quick. And then finally, when the word quick comes, then we get the full part. But these should essentially be 0. So we can do this by adding a matrix to it. So how do we do that? So let's say we've gotten our similarity score. And for simplicity, I'm just going to name, let's call the start token A. Let's call this B, and let's just call this C. So we've got our ABC, ABC again, and this is before the softmax is applied. What do? We just add a matrix like this: negative infinity, 0, 0, negative infinity, and then 0, 0, and 0. Now you might be wondering, why do we add negative infinity? So when we take the softmax function, essentially, when we apply it to the row, these essentially become 0 because e to the power of negative infinity is essentially just 0. So that's why we use negative infinity, and we add it before we apply the softmax layer. So this way we get the exact desired output after we apply the softmax. When we have our ABC, this will essentially just have a probability of 1. Then this will have some random probability after softmax. Let's just name 0.67, 0.33. This will be 0, and then this will be whatever it is. It should just sum up to 1. So let's just do 3, 2, and I think this will just be 0.4 then. Yep. So we get our exact desired output when we have our start token A. It only sees that. Then when quick comes, it sees the previous one, which is A and B. And then when quick comes, it sees its previous, which is the start token, and then quick. And obviously each token sees itself. So brown. Oh, sorry. The start, the, and quick. So this is why we need masked attention. It basically prevents your model from looking into the future and just seeing the answers. So as we go step by step, as each token comes, its previous context remains, but you don't have its front context, the future essentially. And this is very important again because your training loss just becomes zero and your model is not learning. You've given it its answer sheet. So there's no point to it. This is exactly why we need masked attention. So now let's look at the overall view of the decoder block. And I'm not going to touch about layer normalization, the feed forward network and everything again because we covered this in the last video. So I recommend you guys watch that. Anyway, let's head into this. So here, this you're going to see is going to be a lot of the same structure, just a few differences. So your input is your decoder input. Same, you got your batch size, your context length with respect to your decoder and your embedding dimension. So that gets fed into a masked multi-attention head. After that, you've got your layer normalization, and here you've got your residual connection. Let me just highlight that. Here, this is your residual connection. Then after that, you got your cross attention head. Essentially, what that is this whole process is actually called cross attention. Cross attention is essentially the same as regular attention. The only difference is you get your query from this output over here, and your key and value comes from your last encoder block, not the ones at the start, but right at the end. So that gets fed as your key and value. It's the same input that gets fed in. Then you got a layer normalization here. This is your residual connection again. So that gets fed into your feed forward that goes into your layer normalization. And here we've got another residual connection. And then this whole process gets repeated a number of times. How many ever decoders you want to have, you just combine it. And yeah, essentially this is the whole flow of your decoder block. Now let's move on to the LM head. So the LM head is the last piece of theory we'll be talking about in this video, and we can move straight to the code after this. So after your decoder, let's consider this as your last decoder block. It's gotten its input, and you've got your output. And your output, the shape is going to be your batch size, your context length, excuse my handwriting, and it's going to be your embedding dimension, your embedding dim. But what do we ultimately need? Suppose we have a vocabulary size of 50,000 words. This is our vocab size. So we need the probability of which word is going to be in the vocabulary. So we need 50,000 probabilities. So how do we do that? So that essentially the function of is what the function of your LM head is. It takes in your embedding your batch size, context length, embedding dimension, and it converts it into your probabilities. So in this case, 50,000. So our desired shape is going to be our batch size, our context length, and our vocab size. This is the shape that we need. So how do we do this? We can achieve this using a simple linear layer. So we have a bunch of neurons. This is your decoder output. Let's call this decoder output. So this is essentially going to be embedding dim. So the number of neurons is going to be whatever your embedding dimension is. And this is going to connect to another layer of neurons with vocab size as the number of neurons. And all of these are going to be connected. There we go. I'm not going to connect all of them, but yeah, essentially all of them are connected. And this we're going to feed into our softmax to get our probabilities. So that essentially is your function head. It takes your decoder output and converts it into probabilities with respect to our vocabulary size. And that's it. That's the whole process. Now we've gotten the entire transformer. We've covered the inputs, the encoders, the outputs, the decoder. And now we've finally gotten our ultimate goal, which is what is the probability of the next word. So now let's look at the code And in the next part, I'm going to tie all of these concepts together. So don't worry about that. It'll make a lot more sense. And I'm going to take a nice big sample data set so it's easy for you to understand, as well as you'll get the full encompassing picture. So let's get into the code for the decoders for now. All right, now this is the part that I'm sure you guys have been waiting for, the coding part. So here I've already typed out everything. Unlike the previous parts, I'm not going to type it as we go because a lot of this code is similar to the previous one with just few minute changes. So first, let's look at the encoder. It's going to be essentially the same code. We've got our attention head. The only difference in this code is we've taken a new input called masked. And if it's true, we apply the masking, where we take in that extra matrix and we combine it, we sum it up, and then we run our softmax over it. So this code essentially does this. It takes in your extra, the negative infinity matrix, and adds it to your similarity score. And here, I'm going to print it out just so that we can see. So we can print our masked output. And let's print our similarity. And after this, let's print our masked output. Not output, sorry, our similarity. So let's just add that, our masked similarity after softmax. And we're going to change this to scaled similarity. There we go. And our decoder, again, everything remains the same. And finally, our decoder, what we're going to do is we have a cross attention head. Again, it's the same process as a regular attention. The only difference is, I told you, our K and V comes from your encoder's output. Then we have the cross multi-attention head. Again, same process, only difference is K and V come from your encoder output. Same forward pass. Then we got our block. So for our block, we need our masked attention. We've got our cross attention, our feed forward, and our 3 residual layers, our normalization. So here, not residual, sorry, a layer normalization. And in the forward pass, here we add our residuals, X plus your self-masked attention. And then again, we've got this, the second residual connection, and then your third residual. And finally, we get its output, the decoder blocks output. And your decoder essentially is just a list of your decoder's blocks. Now, here I've told you that most of the code is the same. So that's why I've already written it out already. I'm sure if you even look at it, you can see that literally majority of it is the same. So to save time on this video, that I've decided to just type it out beforehand. And finally, we've got our output layer, which is our LM head, which converts it into our probabilities of vocab size. Hence, we've got the linear layer. And finally, here we can run this code. We've got our encoder, we've got a decoder, and our output layer, we got our embedding dimension and vocab size. So here we're going to print all of this, and let's see what we get. So I'm going to run the code. I'm going to pipe it to output.txt, and I'm going to show you. So as we can see, we got our masked similarity and our masked similarity after softmax. Oh, sorry, that is my mistake. No, wait, this is the encoder. My bad. This is why they're not masked. Let me just add an if-else statement. Give me a second. In our encoders, there we go. I'm going to do this. And again, or actually, let me just have this written out again. And there we go. Now let's run this. Let's run it again. Yeah, there we go. So now it's showing only the decoders. The issue with the previous one was it was printing it even for the encoders, and there we didn't actually have the masked similarity. So there we go. We got 0.24, our negative infinity. And then after softmax, we get our zeros. So this happens a bunch of times. And finally, we can verify the shapes. And ultimately, we get our probabilities, which will be of the vocab size, our batch size, context length, and vocab size. So yeah, there we go. That's how this works. And hope you guys enjoyed this video. This is a relatively shorter one. And part 4 is where I'm going to tie up everything together. And we're going to be copy pasting quite a lot of code. So it's going to be very similar and it's going to give you a good brush up as well. But I'll just show you how these concept gets tied and the back propagation part of it. So once we get our probability outputs here, that's the forward pass, we're done with that. Then we calculate our loss function and then we do back prop. So all that I will explain in the next video where I show you the real life example. But for now, we are essentially done with this video. So let me head back to OneNote. I don't know if you guys can see it. Just give me a second. Yeah, you should be able to see it now. And yeah, we are done with part 3. So we can move on to our final part, which is part 4, where I'm going to be showing you the working example.